So now for something completely different, we're gonna speak about how to generate a very low phase noise microwave signal from optical reference cavities with frequency combs. So this is a presentation on behalf of a quite large collaboration, and due to the facilitated founding of French Research Institute, this is the most difficult slide I had to prepare today. And so why do we want to generate low phase noise microwave signals? So there are a number of applications for microwave signals, and for the metrology community, one, it's the interrogation of atomic fountain clocks, and there are another number of applications that are related with the synchronization of large experimental facilities, from a very large baseline interferometry to particle accelerators, telecommunication systems, and there are other applications. So there are a number of very good sources of microwave signals that range from room temperature sapphire oscillators, cryogenic sapphire oscillators, and optoelectronic oscillators. So what you want to do with with photonic generation of microwave signals is to do better than all those. And the idea is very simple. We take the best oscillators we ever realized. That there are optical oscillators, lasers stabilized through ultra-stable cavities, and we use optical frequency combs to divide their frequency from the optic domain to the microwave domain. And in this way, we obtain a division of the frequency, but also a division of the phase noise by a quite large number. So here I plot the performance, I would say standard performance of a number of microwave sources, and here I project what will be the phase noise of a microwave signal generated by frequency division of a kind of, okay, it was state of the art a couple years ago. Now it's a modest optical cavity, and the dot line here would be what we'll be able to do if this cavity would be working at its thermal noise limit. So if we are able to realize the system, we can provide a microwave that has very low phase noise, both a very small frequency offset from the carrier and a very large frequency offset from the carrier. How we do that is kind of easy. We use a cell reference optical frequency comb. That's a device that outputs a comb of spectral lines. Each line can be identified only by 3 numbers: the line number, the repetition rate of the comb, and the offset frequency. If the comb is self-referencing, I can take the low part of the spectrum, do second harmonic generation with it, beat it with the high frequency part, and extract the offset frequency. I can simply measure the repetition rate, shining the comb on a photodiode. The comb can be locked to an optical reference, simply taking one of the lines, beating it with the laser field from a reference oscillator, measuring this beat note. One of the things we do in the specific implementation of this technique is that we don't stabilize the parameter f0, but we measure it and we subtract it from our beat note. Then we get a beat note that's independent of f0. We can stabilize the frequency of this beat note, act with a control loop on the comb, and obtain the stabilization on all the lines of the comb. This technique implements actually a virtual comb that has a null offset frequency. In the generation of microwave, we simply take the system, we shine the comb on a very fast photodiode, and we extract a microwave signal after filtering. As we will see in the following, while the performance of the comb and the performance of the optical cavity are important, a low Fourier frequency the process of photo detection is the process that introduces the most phase noise in the system, and is there where most of the work is gone to produce the results that we present later. So the system looks a bit like that. So we use a comb that's based on a commercial product from Mello Systems. We use high-power photodiodes from Discovery Semiconductor. We have a 250 megahertz repetition rate comb that's centered around 1560 nanometers. We have octave spanning after broadening. The important thing to highlight here is that we have an intra-cavity electro-optic modulator that allows fast actuation on the repetition rate of the comb and then tight locking of the comb to our optical reference. And I also need to point out that this is a very simplified scheme of a femtosecond oscillator. What we use in reality, it's a new Mello technology that's the figure 9 comb, for which I don't have a diagram, so I represent it like this, but it doesn't look like this probably. There are a couple of fundamental noise limits in generation of microwave. The first one is a thermal noise. So whatever we're gonna do with the microwave we generate from the photodiode, we're gonna have to make it go through some kind of microwave circuit, and this microwave circuit will be impedance matched, usually a 50 ohm, and this impedance matching, with impedance matching of this kind is inherent to have some thermal noise, Johnson-Nyquist noise in the resistance that composes the microwave circuit. And the other limit is the shot noise. So the quantum nature of light and of charge carriers introduce what's counting noise and then shot noise in our system. Both those noises scale with power. So if we want to beat those limits, we need to have an high power signal. And to obtain high power microwave signals, we do two things. The first thing we do is to amplify quite a bit the output, the optical output of the comb with an RV-dop fiber amplifier. And the second thing we do is pulse rate multiplication. So our comb has a repetition rate of 250 megahertz, but we want to detect microwave signals. We want to detect microwave signals at 12 gigahertz. So we have a lot of spectral content in the microwave signals at the harmonics of our repetition rate we don't really need. So the trick is very easy. In principle, it's a bit harder to realize in practice. So we simply have a cascaded pass interleavers. What we do is simple. We take the light output of the comb, we split it, we introduce a delay in one of the arms of this interleaver, and we recombine it with one half of the light shifting time by half the repetition, half the time between two pulses. Doing this 4 times, we get 16 times repetition rate multiplication of our comb. This allows us to increase the power at the harmonics of the repetition rate that are important for our application. One thing to point out that doing that with common fiber optics, it use some inevitable losses in the components, but also a 3 dB loss that's inherent in the fact that we have a splitter. And the main noise contribution we need to fight in the generation of microwave from an optical signal is the conversion of amplitude noise into phase noise in the photodetection process. So because of saturation and due to mostly space charge screening effects in the photodiode, the response to the photodiode is highly asymmetric at increased optical powers. So you see here, for a low energy pulse, the response of the photodiode in time It's on a very nice pulse. When I go to very high powers, I get a very asymmetric response, and this causes a conversion of amplitude noise, so changes in the peak power here, to phase noise, so a change of the time position of the harmonic of the signal I'm trying to extract. So there are two ways to reduce the importance of this effect, the microwave extraction. The first one is to reduce my amplitude noise, so there is less that can be converted into phase noise through this process. And we have already a very nice intensity noise figure here due to the use of very low noise optic amplifier that actually reduced the optical intensity noise from the comb. And on top of that, we also implement an active intensity stabilization, simply monitoring the microwave output of the photodiode and putting some feedback in the system. The final reduction of this effect comes from the observation that the amplitude to phase conversion in the photodiode depends on many parameters. Mostly depends on the optical power on the photodiode, and then on the photocurrent used by the photodiode, and on the bias voltage. And we have, fortunately, an operational point, where the amplitude to phase conversion is actually 0. Then we can implement a scheme for the active stabilization of the working point of the system to this magic point where the amplitude to phase conversion is 0. So here I try to highlight very quickly how the system works. Up here we have our optical frequency combs locked to our auto-stable laser. We go through a zero-order acousto-optical modulator that's used as an intensity modulator, and we introduce an amplitude modulation tone on the intensity of the light pulses from the comb, and we shine this to our photodiode used to generate our microwave signal. Through a bias T, we are able to detect the amplitude and then know what's the effective amplitude modulation we are putting on the light. And we extract the microwave part of the signal. We beat it with a microwave reference. We extract the phase component of the modulation. So we have the measurement of the amplitude modulation, and through heterodyne phase detection, we measure the coherent phase modulation. We go through some digital signal processing where we demodulate those two signals. We do the obvious division of the phase by the amplitude to get the amplitude to phase conversion coefficient. We implement a controller that acts on the acousto-optic modulator to keep the power emitted by the optical system at the magic working point where the amplitude to phase conversion is 0. One final trick we need to implement to have low phase noise production from the system is to have optimal duration of the optical pulses. And unfortunately, the system is composed by a sensible amount of fiber length that introduce dispersion, mainly in the erbium doped fiber amplifier used to increase the optical power, and then in the Mach-Zender interleavers that are used to increase the repetition rate of the comb. Then we need to introduce an equivalent amount of negative dispersion to recompress the pulses and have optimal pulse duration. We experimentally derived that our phase noise strongly depends on the duration of the pulse, but not all the components going to contribute to this noise are completely clear at the moment. For sure, there is a strong dependence of the amplitude to phase conversion on the pulse duration, but that's not completely clear, of not completely clear origin at the moment. The final problem we need to solve to demonstrate a very low phase noise performance is to find a way to measure the phase noise. So we are trying to beat the phase noise of every other oscillator around, so we cannot really compare directly our system to another one and extract the performance of our system. The common thing to do in those cases is to have another identical system, compare the two, and simply assign half of the noise to each system. This is the drawback that we actually need two very good noise microwave sources, and it's cumbersome to put them together in the lab. And also, this assumes the equal contribution from the two. And in a very complex system like that, it's very difficult to be completely sure that the two systems really are working with the same performance. So the final thing we need to be worried about, since we are generating microwave from an optical source as an inherent high, relatively high intensity noise, is amplitude to phase conversion in the measurement system itself. So we decided to go for an heterodyne-based cross-correlation phase noise measurement system. This requires two extra auxiliary uncreated oscillators to be compared with the good one we want to characterize. But the good thing is that the phase noise of two auxiliary oscillators only affects the uncertainty in which we are able to estimate the phase noise of the device under test, and this basically only increases the integration time required to reach a given uncertainty we want to demonstrate at the performance. So how does the cross correlation scheme we implemented work? So here is our device under test. So here is a optical frequency comb that's locked to optical cavity, for which we measure, which we detect the pulse train with the schema I presented before. And we have two almost identical systems that I use to derive two heterodyne B notes that are then sampled and processed. I will describe later. The important thing here is that those three systems here need to be completely uncorrelated. So all those three are three different combs locked to three different optical cavities. And the sampling of the signal generated by the mixing of those three needs to be sampled with uncorrelated clocks. Otherwise, I would be transferring the stability of the clocking the sampling system to the measurement you want to do. So in more technical details, we implemented a system that's based on an FPGA equipped with a very fast analog digital converters based on an analog device, clocked analog device ADCs with 12.5 noise equivalent bits of sampling resolution. We clocked those at 250 megahertz through some very good quartz oscillators. We acquire the signals from the ADCs with an FPGA that performs digital down conversion of the bit notes to a frequency that's more manageable for data transfer to an OS computer that performs the cross correlation. We extract the phase noise, and that's what we get. So the blue curve here is noise performance of the system we put together, and here I'm trying to compare with state-of-the-art performance of other systems. And it's clear that we are beating the performance of all of them in all frequency bands. And that's probably the lowest phase noise microwave signal ever generated. And we are limited here at high frequency by Sharp noise, limited at a very low frequency by the thermal noise of the optical cavity we are employing to lock the comb. There is some excess noise in this area that's under investigation. And some excess noise here at high frequency, but this is an artifact of the bandwidth of the lock of the comb to the optical cavity. And with this, my conclusions.